Hello, everyone. So today we're going to be continuing our conversation on equilibrium by talking about how equilibrium can change when I put it under external perturbations. Most specifically, we're going to be looking at changes in temperature and pressure. So if I'm going to go ahead and try and determine how equilibrium is going to change, one of the good places for us to start is our classic equilibrium equation of relating our equilibrium constant to our standard state free energy. But again, one of the big questions that we may end up having is how is this equilibrium constant and our equilibrium itself going to change if I apply a pressure? So if I apply an external pressure to the system. And just like we saw with applied pressures in pure phases, it highly depends on the system we're talking about. Because if I'm an ideal gas, we tend to ignore any applied pressures because, again, ideal gas only cares about the pressure or concentration of its own species. So if I add an additional pressure of something else, it don't care. But again, as always, it's worth noting that real gases are a little bit different. And again, for real gases, this is entirely going to be in terms of the fugacity expression. So this is going to be our fugacity constant, which itself will be changed. But the overall K itself won't really change. All we're going to be seeing is this change in the fugacity portion of the equilibrium expression, which can again be calculated from tables. However, things get a little bit more interesting if we take a look at if I'm applying how I apply the pressures. Because in practice, if I'm applying an external pressure, what this often does is going to be increasing the pressures of the individual components. So I'm increasing essentially the total pressure of the system. So I'm going to see some change of the individual components. The classic ways we can imagine this happening is either by reducing the volume of the system, at which point, since everybody's volumes decrease, and we're going to assume a relatively closed system, pressures increase. Similarly, we'll also see a change if I change the temperature. This will also manifestly change the pressures as well. And if I'm looking at changes of individual components, what we're going to see is that the overall equilibrium constant won't change. But what we're going to see is since the pressures change, we're going to see essentially effects that follow the Chatelier principle. If I'm net increasing the pressures of the products more than the reactants, number of products increase, so I'm going to essentially drive it to the left. If I increase the number of reactants, I'm going to essentially drive the reaction to the right. And again, we can imagine looking at this in a more kind of concrete example by looking at essentially the thermal decomposition of dinitrogen tetroxide, which can decompose to NO2. So in this case, we're going from 1 mole of reactant to 2 moles of product. So what we can do is see what happens if I half the volume. Well, we can start with the idea of our equilibrium constant, literally being the pressure of our product squared over a reactant. Now, if I half the volume, I'm going to be doubling all of my pressures. So in this case, what's going to happen is that since I have this squared for my nitrogen dioxide products, I now have a precursor of 4, 2 squared over 2. So what I've done is I increased my reaction quotient. I essentially now have a net larger Q than my equilibrium K. So as a consequence, we're going to see the reactant shift towards the reactants in order to try and stay at equilibrium. And this is how a lot of effects of applied pressures in gas systems work, is it mostly functions as a change of the concentration. However, things can be a little bit more tricky when I'm looking at, say, something like a condensed phase. So if I'm looking at condensed or aqueous phases, here applied pressures can actually be a little bit different. So in these cases, we can look at the changes in equilibrium constant by, of course, looking at changes in our free energy. So in this case, we can imagine the change in my free energy will be given by the change of my standard state free energies. So again, this is going to be my standard state reaction energy, plus the correction for the free energy by the applied pressures. And again, here we're using the model of a condensed phase where free energies should change linearly with pressure, but again, modified by molar volume because we're after a molar property, and again, the stoichiometric coefficients. If I'm generating a lot more of a species, even if it has a smaller molar volume, this can drastically shift the equilibrium. And so what we can then do is assume that since the K has no terms inside that accounts for the change in effective concentration of our system. Instead, it's going to be modeled as the effective change of our new standard state free energy. So my whole term of RT ln K is now going to be equal to my new free energy term. So again, we're going to see a slight modification of our equilibrium constant. But again, as we've seen previously, in order to have substantial changes of our right-hand side, we're going to be having to look at typically very large volume changes, very large pressure changes, or more frequently, both. But in general, what we're going to find is that as I increase my pressures, I'm going to tend to favor my more compact phase, so the phase with the smaller molar volume. However, what often ends up being much more relevant is how our equilibrium constant is going to change with temperature. Because as you may have noticed, it's right here in the dependencies. So we don't have to really dive on how our standard state free energy might change, like we do with applied pressures. Instead, I'm going to have to simply model how this inverse relationship of temperature with equilibrium constant may end up changing said equilibrium constant. And not too surprisingly, if I'm looking at how my equilibrium constant changes with temperature, my go-to dependency is going to be taking the first derivative. So I take the first derivative with respect to temperature. R is going to be a constant. And then we run into this pesky problem. I have an inverse relationship with temperature here, but we've also previously shown that free energy also has, or reaction free energy also has a temperature dependency. So at this point, I now am looking at the change in more or less my total entropy with respect to temperature, which hopefully should get some wheels turning in the back of your head because it's been a couple of chapters, but this is our Gibbs-Helmholtz equation. It makes an appearance once again. And so what we find is that our whole derivative here is going to be the same thing as the negative of the change in the enthalpy of reaction over temperature squared. And then we essentially bring our R back in. And so this condensed form of relating our natural log of our equilibrium constant to our enthalpy of reaction is more commonly known as the Van't Hoff equation. And we've dealt with similar approaches when we were looking at the temperature dependency of phase changes. It all derives from the same basic application of the Gibbs-Helmholtz. So what's really important about our Van't Hoff equation is it's going to show a lot of our dependence on the enthalpy of reaction, or a good way of looking at it is the exothermicity. So what happens if I've got an exothermic versus an endothermic reaction, and what effect is that going to have on my equilibrium constant? Well, a good way to do that is to try and isolate my equilibrium constant on the left and all of my temperature dependence terms on the right. So here we're actually fairly lucky because R is always going to be positive. Since we're working in temperatures in Kelvin, this is always going to be positive. So our only two components that can change signs are enthalpy of reaction, could be exothermic or endothermic, and the change in temperature. So let's go ahead and split this case in half. So if I have an exothermic reaction, it means I'm going from a high energy to a low energy. And in practice, this means I'm going to have a negative change in enthalpy, which means that if I have an increase in temperature, so a positive temperature, and a negative change in enthalpy, this means I'm going to have a negative natural log, which is essentially a way of saying that I'm going to decrease my equilibrium constant. So the equilibrium constant is going to decrease, meaning it's going to become lower, also meaning it's going to be more reactant favored. And we can also examine this same idea from a more kind of statistical mechanics perspective. So if I have an exothermic reaction, it means my reactants are higher in energy, which means at low temperatures, I don't want to be at the higher energy state. But our Boltzmann distributions do show us that as we get to higher temperatures, we're less likely to occupy the lower energy states, and entropy makes it more likely that we're going to occupy the higher energy states. And this is exactly what we see with reactions, that as I increase temperature, I'm more likely to occupy the more unfavorable enthalpic state, in this case, my reactants. We see a very similar but inverse trend when I'm looking at an endothermic reaction. So now I've got a positive change in enthalpy as I'm going from low energy to high energy. So naturally, we think of this as an unfavorable reaction. So if I have an increase in temperature, positive plus positive, means a positive change in the natural log. So my natural log is essentially getting bigger, which means my equilibrium constant is getting bigger, which means it favors the products. So again, endothermic reactions, higher temperatures favor products. So a way to look at this is that my products being higher in energy means that according to our Boltzmann distribution, the higher the temperature, the more likely I am to occupy these higher energy states. So I'm more likely to land in a product state, thus meaning it's easier to form a product species. And this is exactly what we expect to happen. However, this just gives us a general idea of what trends we expect our equilibrium constants to fall under for exothermic or endothermic reactions. It can also be very useful to try and take our Van Hoff equation and actually use it to determine numeric changes in the equilibrium constant. So if we know our enthalpy of reaction, we can simply integrate our Van Hoff equation to determine how our equilibrium constant changes. So the integration of the right side or the left side should be fairly easy, as at this point the integration of natural log of k should be fairly dnl of k should be fairly trivial, because it's just going to be ln of k end state minus initial state. Whereas over on the right side, well, this one is still not exactly unfamiliar. Enthalpy and the ideal gas constant are both going to be held constant, so I'm going to pull them out front. And we have the integral of 1 over temperatures, of dt over temperature squared. So this gets us negative t, again, end state minus initial state. Now we can do our usual trick with natural logs, and we're going to find that we have the natural log of the ratio of our equilibrium constants is going to be equal to the negative of the enthalpy of reaction over R, to essentially correct for my units, times essentially the difference in the inverse of temperatures. So again, this will end up producing the same general trends that we just illustrated. But let's take a look at what this looks like. So let's go ahead and take a look at one of my favorite chemical reactions. This is the Born-Haber process. It's how most ammonia is made made in modern industry. So if you use an industrial fertilizer, this tends to be how you produce it. You essentially take nitrogen, you take hydrogen, and you feed in a whole bunch of energy. And this will essentially generate ammonia. So this reaction has a K of about 6 times 10 to the 5th, so fairly favorable, and is an exothermic reaction. So again, we expect this reaction to be favored for lower temperatures, which might make it surprising the fact that the reaction is actually run at 500 degrees Kelvin. So in order to try and figure out what my equilibrium constant is at this new higher temperature, I can simply rearrange my Van Hoff equation, raise both sides to the exponential, so raise it to the power of e, and then multiply it by my initial equilibrium constant. And at this point, we get an equation that's going to be a fairly useful modification of the Van Hoff. where my equilibrium constant at my new temperature is going to be equal to my equilibrium constant at my old temperatures plus the exponential of, again, this variance with temperature. So when we go ahead and we plug in all of our numbers, we have an exothermic reaction, so our negative signs annihilate. Our units will end up annihilating the exponent. Again, please make sure that you put both in the same value. A common mistake is to put your enthalpy in kilojoules and your R in joules. Make sure that they're either both in joules or both in kilojoules. And then again, we have the difference in temperature. So when we do this, we find that our equilibrium constant is now 0.18. So again, we saw exactly what we expected for an exothermic reaction. I increased the temperature and the equilibrium constant decreased, largely driven by 1 minus a large number minus 1 minus a smaller number is going to tend to give me a negative value. And that's going to dominate this decrease in the exponential function. So we now have a k that is much smaller. So for some reason, we run a reaction at high temps and make it less favorable in order to make the process occur. This is a good way of showing that equilibrium constants may not always be everything, because it turns out that this reaction runs so slow at lower temps that in order to get it to run at any reasonable rate, you have to elevate the temperature to about 500 degrees Kelvin. And you have to use a lot of tricks to essentially produce enough ammonia. But again, this really shows that while equilibrium is useful, we also need to account for kinetics, which is going to be next chapter. However, next up is going to be a quick interlude in another method to monitor chemical equilibrium, and that's going to be electrochemistry. Until next time, take care.